Have you ever thought about the fluidity of space-time? Me neither. So let's dig into it. What's up, dude?
Nothing. I'm ready for this.
So the way I'm going to do this is I'm actually just going to straight up ask you kind of your background and just how you're qualified for this. So go for it.
All right. So I am a third-year undergraduate student in my first year of undergraduate studies in the sciences. So I'm studying physics, astronomy, mathematics, and computer science. As far as popular science podcasts and stuff, I've listened to a lot of that. I've paid attention to a lot of pop science speakers. That's how I got interested in science to begin with. As far as like my actual completed education goes, I'm far from an expert, but that's kind of why I'm taking notes, because I want to be able to say like, oh, you know what? I didn't know what I was talking about when we talked about this. I'll circle back to it, and we can figure it out like whenever I'm less dumb.
For sure. Yeah. So, I mean, realistically, though, you've always had a passion for this sort of thing. I mean, physics and fucking, astronomy and all kinds of shit.
Yeah. I mean, at least ever since I was like graduating high school, I think like I got out of high school and kind of discovered Star Talk Radio and Philosophize This podcasts, and it kind of kicked off this like learning kick, and I just wanted to learn stuff on my own. And yeah, I've been passionate about it for probably about 10 years.
Right on. Okay, so what I want to do here is present you with a theory that I have come up with on ChatGPT or GPT.
Okay.
And basically just see what you think about it and see if you can either disprove it or just basically beat the AI in this sort of thing here. So, yeah, let's test your knowledge. Okay, so it's the superfluid spacetime theory. What if spacetime acts like a superfluid and black holes are like waterfalls pulling it down? This could explain why time slows down near them, just like water speeds up at the edge of a waterfall. Gravitational waves could be ripples in the cosmic fluid, and dark matter might be invisible currents we can't see but we can feel. If black holes drain space-time somewhere, what's on the other side?
The truth is, I have absolutely no idea. I have no idea, A, why you would assume that space acts like a fluid. Like, in what other areas does space act like a fluid, right?
Right.
So the average density of space is less than 1 atom per cubic centimeter. So I'm trying to like understand how it's even possible for something that is lacking anythingness to have some sort of fluidity to it. Does that make sense? So that's kind of like one part of this where I'm like, I don't even know that it's possible that something that is literally defined by being nothing can have fluidity.
No, yeah, I understand that, but I mean, being nothing and not knowing what it is would be the same thing almost. You know what I'm saying?
No, it's because we do know what's in space. Space is literally distance between things.
Right. Okay.
So
okay.
So we know we have like dust and like hydrogen and like there's random spots of like carbon and nickel and iron and like all floating around in like little tiny grains of dust. But there's so little shit in space that there is literally, okay, so like, how many grams do you think this is?
8?
I don't fucking know, but it's not 500, right? It's not 500 and it's not 0. So so there's something on the order of like, for every 1 gram that this is, there's 6 times 10 to the 23 atoms here.
Okay.
And this is at least 10 grams. This itself, right? This
Right.
pin.
What's your point?
Okay. So I'm saying that you got something that's got 6 times 10 to the 24 atoms here.
Yeah.
Space has 1 atom in this distance on average. 1.
Oh, okay. Really?
Yes. It's incomprehensible how little stuff there is in space.
Okay, yeah, I mean that's something for sure.
So there has to be some relationship between the random ass floating stuff that's in space,
right,
for them to act together as a fluid for this to work. And it's like, why would you, like, for what purpose would you ever assume that a bunch of nothingness is acting together as an organized fluid?
I see what you mean. I mean a simple way to look at it from a simple-minded human would be like, I mean, why would shit orbit anything else in just a fluid sack? Right? I mean, that would be something weird to think about.
So what you're saying is, in order to disprove that space is a fluid, is that you would think that there would be some sort of slowing effect, that you were like going through and you're getting like a drag or a resistance by moving through some sort of fluid, right? Is that what you're saying? So that like orbits would decay differently.
I'm saying that there wouldn't be an orbit because nothing would be dragged to the mass, because it wouldn't be dependent on mass. If you literally had a water balloon full of water and you put dirt in it, without gravity, why would anything orbit something else?
So you're telling me that this theory, that I'm misunderstanding it, and what it's actually saying is that gravity is actually the side effect of this unknown thing. Is that what you're telling me? Is this unknown thing of space acting like a fluid, and that all motion is directed toward black holes?
See, that kind of sounds like it, right?
Is that what you're telling me? Because that is bunk.
That's bunk, right? Yeah. No, that's totally bunk. And that's what it sounds like. That's what it sounds like after, talking about it. But, yeah, that's what I'm thinking it's saying. Yeah, that all movement is towards black holes. But what I'm thinking now, though, how this kind of came out in my brain is I was only thinking about time dilation. So that's where the fluid thing came into play for me. But and then I just had ChatGPT help me out with the idea. So they kind of took that as well. And so they're probably, yeah, that's probably what debunks it.
Well, no, I'm really curious about, like, so the whole theory, so I thought that it was explaining a part of, like, it's suppose that space acts like a fluid in high density regions where there's this supermassive thing hanging out. And this supermassive thing influences the curvature of space-time, but space actually slips into it at a different rate than you would expect. So it's kind of like trying to come up with this solution to more of like a dark matter, dark energy problem than it's trying to come into like solving all of gravity.
So the first key proposition of the hypothesis here is time dilation and viscosity of space-time. So the way it states it, the way ChatGPT states it, is time dilation near massive objects is analogous to the viscosity of a superfluid, where space-time stretches when it's near mass and scrunches when it's falling into the black hole. So in a manner of similar to fluid dynamics.
You've got a mass, we'll call it the sun so that we can imagine it, and you're saying that in the presence of mass, space-time expands?
It stretches, yes.
It stretches. And by stretching means time slows down?
And this is all about time dilation. So yeah, it would be time slows down, yeah. That doesn't make sense then, huh?
Okay, no, that's fine. I mean,
Okay.
in the presence of a black hole, also, that's fine. Yep.
Okay. And then on the other side, it scrunches when it's going into the black hole. So when it speeds up when you've gone inside of the black hole.
So the idea of this whole theory is that a black hole is actually a puncture wound in the fabric
Yes,
of the universe.
exactly.
And it's the stuff from the universe is going away to
Right.
some unknown place.
Yep.
Okay.
Yes. It sounds, dude, the way you say it, it sounds way worse than it is.
Okay. Okay. All right, I'm starting to understand where we're at here.
But that's just the. I mean, do you have stuff to say about that? Because that's just the first proposition.
Okay. Yes. So first of all, one of the major components of physics is that matter and or energy, because we consider them to be the same thing, right? Or can be the same thing. And so everybody in the world is familiar with E equals mc squared, right?
Right.
So when you do like nuclear reactions, they have the combinations of atoms. If you take a mole of hydrogen and you fuse it together and you get helium, there's a mass difference. It loses mass in the process of becoming helium, which is what our sun does all the time. And then that loss of mass actually is a transfer into energy. It releases energy.
Right.
That whole process works because all of energy and mass or matter is constant in the whole of the universe. So it's not just locally constant, but it's constant everywhere. That all the stuff that exists in the universe doesn't go away. It just gets turned into other stuff. There's this process of entropy, of it becoming cooler, denser stuff, right? So that's kind of what our whole basis of cosmology and physics says, right? So if we take that matter is going into a black hole and then it's getting transported to another dimension or entering a different universe, we're destroying matter. We're getting rid of energy.
Just talking about that, though, I mean, how this might be a stupid thing, but how could the universe expand if there's no growth? You can't get rid of matter, but you can't create new, right?
So you already know that space is incredibly not dense, right? Like it's a huge nothing. There's a bunch of not anything in between us and anything else, right?
Yeah.
So what happens is that on cosmological timescales, the amount of not anything between us and another thing gets bigger.
Okay.
It gets further away. There's not anything more in between, but the density, the average density, actually decreases.
Okay, that's strange, dude. I'll write that one in a book.
I mean, honestly, hell, dude, if I could tell you exactly why the universe was expanding, I'd get a Nobel Prize. I'd go collect it tomorrow. I'm just telling you, that's what we see, right? Like we look into the Hubble constant, and we're like, yep, shit's going away from us. I mean,
there's just nothing.
And in every direction, right? It's not just it's going over that
too.
way. Every single direction,
but
it's going away.
Isn't it? But it's not central to Earth. It's if we were on the moon, it would be every direction from the moon as well.
Yes.
Yeah, that's fucking weird to me.
Okay.
Yeah, I don't like that.
All right, so think of it this way. There's not any special reference frame, right? So like, no matter where you are in the universe, The universe is not okay. So I remember you sent me this video of this guy saying that the universe is homogeneous. It's not exactly homogeneous. It's statistically homogeneous, but if you imagine that everything that exists now, all of that stuff, all of that matter didn't get summoned out of nothing. It all existed at the time of the Big Bang.
Yeah, okay. But then I see what you mean.
And from that point, things have expanded out and cooled, and things have like come together and fused, and over billions and billions and billions of years, things expand from multiple points. It's not like expanding from this center, but this stuff out here is expanding also. Every point is expanding.
I see. Yeah.
Yeah.
Who's to say, though, that this universe is the only thing that spawned out of the Big Bang?
Nobody.
That's pretty suspect.
Okay. Let's wrap up this space superfluid theory. The question is, why are we calling this fluid-like?
The medium paradox. So a superfluid model implies a medium for spacetime, conflicting with the relativistic concept of a vacuum. It says the lack of observed turbulence.
The fluid-like part is kind of confusing because you would expect that something traveling through a fluid would have some sort of resistance, right? Like when we talked about orbits, you would expect orbits to decay a lot faster.
Right.
Like our satellite orbits decay over time, but like the orbit of the Earth around the sun has been really fucking stable for a really long time. And if it was pushing through a fluid, if there was some sort of resistance that it was meeting, greater than an atom every cubic centimeter, I mean, there's like nothing in space. There's a reason why it's so stable, right? Like there's not a lot of stuff slowing it down.
Yeah, some sort of drag.
Yes, exactly. And then what was the other part? The one I really touched on.
So the medium paradox, the medium for space.
Oh, the vacuum. The fact that it's a vacuum. Yeah. You would expect that there would be some sort of relationship between these things that are really far apart. Like the strong nuclear and weak nuclear force have an effect on each other on scales that are incomprehensibly small, like 10 to the minus 15 meters. Femtometers. Those kinds of forces would have no effect on each other. EM forces also decay at really, really small distances. So those are just singular atoms, right? Like we're talking about singular atoms, if that. And then you're thinking about things acting like a fluid? I mean, really, it's got to be acting like a fluid due to gravitational force.
Yeah, that was my main issue, because it has to be influenced by gravity.
Like, and then why would...
But, I mean, gravity exists. Gravity exists in space, right? With the whole mass and shit, right?
And, well, that's what I was getting at, is like, okay... Maybe, but then it kind of just goes back into the geometry of space-time, because mass influences geometrically space-time. Okay. And then it's like, so at that point, it's redundant. Like, there's no reason to add this filter layer of saying it's a fluid. Because you're essentially saying, like, well, because gravity is making this a fluid, it has this behavior. And it's like, well, we already said it has this behavior because mass influences space-time, like the shape of it.
I love that you said that, because that actually makes me feel comfortable with the conclusion on that. Because there's no reason to add it. There's no reason to add it.
Yeah, there's no reason to add this fluid layer. And then the other thing where you poke a hole in the universe, that it destroys the foundation of all of physics, of the conservation of mass and energy.
Now this says Hawking radiation analogy is another reason why it's challenging to disprove.
No, that just disproves it.
Okay, so
Because
could be interpreted as wait, whoa. Let me tell you what it says. Hawking radiation could be interpreted as evaporation or as an evaporation effect from this fluid comparable to mist escaping from a waterfall.
Okay, so Hawking radiation is this idea that the stuff that goes into a black hole comes out as radiation.
Okay.
It gets turned into energy, essentially. Mass gets turned into energy, and it gets radiated away, and eventually black holes decay because they radiate out everything.
Okay.
Which is kind of like, and I'm going to get myself into trouble if I talk too much on it. So maybe I won't say the next thing that I was thinking. So
Wait, you're gonna get yourself into trouble because you don't know for sure,
I don't know. Well, what I was gonna say is like,
or like the police are gonna fucking throw a flashbang in your window.
yes, no. I will say Hawking radiation. The idea that it exists, I think, has been proved. That we can measure that they are radiating. But the time scale that a black hole would actually disappear is so long, none of them would have disappeared by now. We would not expect black holes at this point in cosmological history to be disappearing, that we can observe them being gone or like being
Right.
at later radiated stages. I think that's the case, but I would have to like actually look it up and read about it. But
Okay.
yeah.
The conclusion here is that the superfluid spacetime hypothesis offers a paradigm-shifting perspective on the nature of spacetime, gravity, and dark matter. While speculative, it provides a cohesive narrative that aligns with certain quantum and relativistic phenomena, warranting further theoretical exploration and empirical investigation.
Oh, ChatGPT says let's debunk it for real. Let's go run an experiment. If you were going to run an experiment, what would you do?
For this,
how would you test that general relativity is not the fundamental science, but actually space is a superfluid, and that's why we see things that behave like relativity? How would you test that?
I don't know. I could ask ChatGPT.
Do it. Yeah, go for it. Because that's really right. Like that's really what we need the answer to, and then we can go run the experiment.
Okay, here we go, man. You ready?
Yep.
Here's how you could approach it: quantum gravity and superfluid models. So this says, let's see what this says. Some quantum gravity models already suggest that spacetime would behave like a superfluid at the Planck scale. Comparing these models to real-world data like high-energy particle collisions could help determine if this kind of superfluid behavior aligns with known physics. What it tests is testing the quantum aspects of spacetime could lead to better understanding of whether spacetime behaves like a superfluid, potentially providing evidence for this theory at the smallest, most fundamental level.
Well, so here's what you said that kind of tipped me off. You said that there's quantum gravity superfluidity models, which means there's people out there that think, who are smarter than me, that are way more educated than me, that think that on the Planck scale there could be this stuff that gets rid of all the problems that we talked about already with the idea of this. So I just went ahead and typed that in and typed for scholarly articles, and there's a paper that talks about all of this stuff. I'll say this: if there's people out there who work on quantum gravity theories that think that superfluid theory is viable, then it's probably viable, and there's probably a lot of explanations for it that I don't understand. But I think on the macro level, it doesn't make sense to introduce the idea of everything being a fluid That's the thing, is if there is a reason to do it, and the reason is that it ties together observations that make sense for general relativity, but also ties together the quantum mechanical realm, then we have definitely, that's a huge discovery in physics.